Hello, beautiful classes. I am going to go through this chapter 9 homework real fast. So this is chapter 9 homework help. I'm coming in from outside, working in some mud, so I apologize. My nails are dirty. I tried to scrub them. They're still gross. Whatever, bear with me, so sorry. All right, so let's go through each one. It says classify each as a Brønsted-Lowry acid or base. Remember, a Brønsted-Lowry acid gives an H+, and a Brønsted-Lowry base takes an H+. Okay. So all we're looking at is which species gave an H+ and which one took. So between these two things, I see HCl and I see NH3, and then over here I see NH4. Y'all see that? It went from a 3 to a 4. This sucker, this one right here, took. So that makes this the base. It took. And I see this started as an HCl, and over here it's just a Cl minus because it gave its H+. That makes this an acid. Remember, the acid and base are always on this side. This side has the conjugates. But, all right, let's keep going. Between here and here, I see that this one had an H, and over here it doesn't, so this one gave. This is an acid. This water right here took on an H+ on this side, and therefore this was the base. Over here, I see that I have an OH minus, but over here it becomes a water, meaning it took, so that's a base. And this was an HSO4, and over here it's an SO4 minus, it gave, it's an acid. Make sure you're paying attention with the acids, or bases, whichever you want, that whenever you give off an H+, you lose a charge, right? Here is a -1, and here is a 2 negative, so just keep that in mind. It's gonna really help you. So same with here, this was neutral, and over here it's a negative, and this was neutral, and over here it's a negative. So when you give off an H+, obviously you lose a charge. It's like if you have $3 and you gave off $1, you'd only have $2 left. So it's always going down. Okay, ammonia, NH3, is amphoteric. That means it could be an acid or a base, or acid and base, depending on the situation. Give the formula of the conjugate acid of NH3. Well, if NH3 is acting as a base, in fact, we can even do this. You don't need to do all of this. But if this is acting as a base, it's weak, so I'd do 2 arrows. It would be taking on a hydrogen from the water. So this would be the acid. This water would be giving it an H, and this would become the conjugate acid. And then our conjugate base would be this water without one. Remember, we have to drop the charge. It would be OH minus. This would be our conjugate base. Okay. So the whole question wasn't really necessary to do the whole thing. It's just asking for that. So this was A. And then B, it says give the formula of the conjugate base. Well, in the same way, what if we switch these suckers up? And what if we said this one's going to be the acid and this one's going to be the base? Well, if we make this one the acid and that one the base, this one's giving off the H+ to this water. So the water would become H3O+. That we got, I hope. But now we've lost a hydrogen here. So this thing lost an H+. So it lost a hydrogen and you lost the positive charge. So what you would have left is NH2 with a negative charge. And this would be the conjugate base. So if you went backwards, this would act as a base and this one would act as an acid. Keeping going. Write the expression for the acid-base reaction that takes place when formic acid dissolves in water. Include the phases. Remember when we were talking about acids and bases, everything's aqueous with the exception of water. So HCOOH, we're gonna lose this front H right here. It starts as aqueous. In liquid water, let's talk what it becomes. So it's an acid. It already told you it was an acid. So what's going to happen is this H is going to go to this water, and we'll get H3O+, and that again is aqueous, plus what's left, which is a COOH, but it has to have a minus charge, and it is also aqueous. Now, the common mistakes I see here are people don't subscript this stuff. You should know to do that. They don't superscript this stuff. So it has to be like bigger, the superscript, the charges. And then you have to use the appropriate AQ button. The appropriate AQ button actually puts us in italics. And it's actually in the homework itself. So like that, when you go to write the text, it pops up and you just click AQ. You're not even supposed to type like the parentheses AQ. You just hit it and it makes it aqueous. So it should be a relatively fast process. All right, moving on. Which acid, A or B, is stronger? Remember, a strong acid, here's what we know about a strong acid. It breaks apart completely, so it dissociates fully in water, right? So if you put some HCl in water, we said it totally broke apart. The other thing about a strong acid is it makes very weak conjugate base. So the stronger the acid, the weaker the base. All right, let's use that information to see if we can figure this out. So A, it says acid B dissociates to a greater extent than acid A, then acid B must be stronger because we know a strong acid dissociates really well. Acid A has larger Ka. Well, if it's got a larger Ka, remember Ka equals products over reactants. If this is a big number, that means we have to have lots of products, meaning it broke apart more. So the larger the Ka means stronger acid. Okay, so acid A has a larger Ka than acid B, then acid A must be stronger in this case. And then in C, the conjugate base of acid B is stronger than the conjugate base of acid A. If in other words, it's saying acid A is weaker. If the conjugate base of this one is stronger, then the conjugate base of this one must be weaker. We know that a weak conjugate base means a stronger acid, and that's, in this case, A would be the stronger acid. Because it has a weaker conjugate base. All right, let's keep going. It says calculate the value of OH minus from the given H3O plus in each solution and label it as acidic or basic. Okay, so, you're gonna have to pause while I go grab my calculator. Sorry, I would edit it, but that takes too long. So you can just wait while I do this, or fast forward. All right. Now we can already guess the answers, but I want to get them exactly right for this stuff. Okay, remember, if you're looking for, it says calculate the value of OH minus from each H3O plus and label it as acidic or basic. There's so many ways we could do this. We can find the pH and then find the POH and then find the OH minus concentration, or we know the following. In fact, let me write them down. I know some of you guys are nervous about this. Again, the front page of the exam is already posted for you, so you can look at all these equations. Nevertheless, we'll do them right now. We started off by talking about the H3O plus concentration times the OH minus concentration. And we said that that equaled Ka, which also equals 1.0 times 10 to the negative 14. Okay, very weak acid. All right, we said pH equals the, P means negative log of, so pH equals the negative log of the H3O plus. We said that POH would therefore be the negative log of the OH minus. We said, doing some math up here with logs, etc., that pH plus POH equals 14. And we also said that if, let's say you have the pH and you want to find the H3O plus concentration, you just take the inverse log, which is the same thing as 10 to the negative pH. So you take 10 and you raise it to the power of the negative pH, whatever that is. And the OH minus is exactly the same thing. Equals 10 to the negative POH. So those are our equations. You do not have to memorize. These are given on your exam. Okay, so now let's go back over here. It gives us H3O plus, and it asks us to find the OH minus. The only equation that has both of those two things in it for the fastest way is this one right here. So let's go ahead and figure out how that would work. Our H3O plus times our OH minus is equal to 1.0 times 10 to the negative 14. It asks us to find the OH minus. So in order to get OH minus alone, we divide each side by H3O plus. In other words, our new equation is that OH minus equals 1.0 times 10 to the negative 14 divided by the H3O plus. All right, so let's go ahead and do it. In A, our H3O plus is 8.8 times 10 to the negative 10. So let me flip it around here. So in A, it's 8.8 times 10 to the negative 10, which means we're saying that our OH minus concentration equals 1.0 times 10 to the negative 14 divided by 8.8 times 10 to the negative 10. Now, when I write it like this, I know that all of this stuff is in the denominator, okay? There are several ways to do it. I like using the division sign there, but for the sake of the majority of people in class, let's do it the way I would normally do it, or where you might do it. So 1.0, you don't need the 0.0, it doesn't change anything, times 10, and then you use the little hat to the, let me put it here so you can see the whole thing, negative 14 divided by, now you need to start your parentheses because you want this whole thing together, 8.8 times 10 to the negative 10, close your parentheses, hit enter, there's your answer. All right, so I get an answer of, let's see, that's 1, 2, 3, 4, 5 times. So 1.14 times 10 to the negative 5. This had 2 sig figs, that had 2 sig figs. In other words, 1.1 times 10 to the negative 5. Let's make sure that's right. 1, 2, 3, 4, 5. Yep. All right. So again, you want to just make sure that your parentheses are like that. All right. Generally, the H plus and the OH minus concentrations, they should add up to close to 14. So I got a negative 10 and a negative 5 that's close to negative 14. So that tells me I'm probably on the right track. That never hurts to do it again. So because I didn't calculate this before, I'm going to do it again just to make sure. 10 to the negative 14 divided by 8.8 times 10 to the negative 10. And I get the exact same answer. Okay, great. Moving on to the next one. Exact same problem. Our OH minus concentration equals 1.0 times 10 to the negative 14 divided by, in this case, 9.0 times 10 to the negative 2. So I should expect something around 12 or 13 because I know that it has to add up to 14. Okay. So here I go again. 1.0, I don't know why I would put the 0.0, times 10 to the negative 14 divided by 9 times 10 to the negative 2. I get 1.1 times 10 to the negative 13, which is exactly what I expected. And this would be in mole per liter, by the way. Remember, brackets mean mole per liter, so same with this one. All right. So moving on, number 6. What is the H3O plus concentration of the following? Well, in order to find H3O plus concentration from pH, we just take 10 to the negative pH. We did this one in class. We did this one in class too, but anyway, so we say that H3O plus equals 10 to the negative pH, okay? In other words, 10 to the negative 2 in that situation. But because this has just one sig fig, we want to make sure that our resulting answer has 1 decimal place is the way this goes. So we're going to say 1.0 times 10 to the negative 2. And that's why we did it in class, because I know the sig figs are kind of funky. So this one will be 1.0 times 10 to the negative 7, and this is 1.0 times 10 to the negative 12. Okay. All right, moving on. Predict the products and balance the following reaction includes states of matter. Okay, so kind of looking to see if this stuff is 1 to 1 or 1 to 2. Remember, this gives off, and I see that we're using hydroxide bases. And that was different than the Brønsted-Lowry bases, because hydroxide bases were like, hey, this sucker gives off an H plus, and this one gives off an OH minus, and remember that it makes water, and then whatever's left. So if this gave off its H plus, and that gave off its OH minus, what we have left is an NO3 negative and an Na plus. Remember, we put the plus first and then the negative, so this would be NaNO3, and that's aqueous. Then we move down to this one. Here we did this exact example in class. Here we have an H plus and an H plus because it has 2 H's, and this only has 1 OH minus, so what do? We need to add another OH minus, so we're going to put a 2 there. And then that thing is going to make now 2 waters. One of those and one of those pair up. And then we have what's left. If we had this thing all together, we had 2 H pluses and 1 SO4, 2 negative. We should recognize that as sulfate. And over here, we had 2 potassiums left over after you took out the OH minus. This is why naming becomes so important. If you're struggling with this, you probably struggled with naming. So go back and study naming more than anything. Okay, if we go to put these together, we have 2 potassiums and 1 sulfate. That works well because the only way we can put them together is K2SO4, and we would call this thing potassium sulfate, and it would also be aqueous. If you ever got stuck with knowing if this was aqueous or not, you'd have to go back to look at the solubility chart and determine. All right, we're flying. Let's keep going. What is the molarity of this HCl solution to neutralize NaOH? Okay, so it's asking for the molarity of HCl. We know HCl is an acid, so it's asking for the molarity of an acid. If this of that, remember that means, the word of means that these two things are stuck together, and it's talking about NaOH. So that means this is the volume of the base, and this is the molarity of the base. Are needed to neutralize this many milliliters of sample. That must be the volume of the acid. Because it's talking about acid is the sample, and it's like, hey, to neutralize 16 milliliters of the sample. Okay, so again, the important thing is recognizing that the of means those suckers are joined together. They have to be both base or both acid or whatever you're looking at. Now, once we did that, we looked at what the reaction was. So we said HCl plus NaOH yields, we got an H plus and an OH minus. We know that yields 1 water, and we know we're left with Na and Cl. Next, we knew that this is a 1-to-1 ratio, right? It wasn't 1 to 2 or anything like that. So we know that the moles of acid, which we know we can write MAVA, must be equal to the moles of base. We didn't need any other number. If this had been a 1 to 2, we would have put a 2 here, or a 2 to 1, we would put a 2 in front of the MA sub A. All right, now we just plug and chug. We're solving for MA. In order to solve for it, we divide each side by VA. Let me do that first. I've learned that lesson. VA cancels, so our M sub A is equal to MBB over VA. Our MB is 0.19 mole per liter. Our VB, because our volumes are going to cancel, we can use the same units. We can use milliliters. Our VB is 36.0 milliliters all over our V sub A, which was 16.0 milliliters. What I mean by the cancel, we take milliliters and divide by milliliters, they go away. All we're left with is mole per liter, and that's good because that's what it was asking for. Okay, so I'll show you how we do it. 0.19 times 36 divided by 16, and I get an answer of 0.4275, or 0.43 mole per liter because this only has 2 sig figs. I'm going to do it one more time just to make sure I didn't make a calculation error. 0.19 times 36 divided by 16 gives me 0.43, and that would be my final answer. Right, so what that means is if we were to titrate some acid, and it said, hey, you used 36.0 milliliters, and the base was 0.19 mole per liter, this was the NaOH. And then in here, you had 16 milliliters of the acid. And remember, for every 1 mole here, you get 1 mole there, and it neutralizes it. It becomes this. You would have to do the titration and then figure out that this concentration right here must have been 0.43 mole per liter. Which of the following species can be Brønsted-Lowry acids? Remember, H plus. They give H plus. A Brønsted-Lowry gives H plus. So if it's got an H plus to give, it's got to be a Brønsted-Lowry. This one does. This one does not. This one does. This one does not. Okay, this one had an H, that one had an H, that didn't have an H, that didn't have an H. Number 10, use the data in the tables to label the stronger acid in each pair. Which acid has a stronger conjugate base? Oh, dang, I need the list of acids and bases. Now I do have to pause it. Darn. Okay, I think I have it from our notes that we did. Which acid in each pair has a stronger conjugate base? If it's got a stronger conjugate base, it must be the weaker acid. Okay, so we got H3PO4 or H3O plus. So here's my relative strengths. H3PO4 is here, and H3O plus is here. So H3O plus is the stronger acid, but we're looking for the weaker acid for this answer, so phosphoric acid. So which one? Oh, it says which one's the stronger acid is H3PO4. Whoa, just kidding. I'm going too fast here. Slow down. H2O plus is clearly the stronger acid than this one because this says increasing acid strength. H3O plus is definitely the stronger acid. So which is the stronger acid is H3O plus. Which is a stronger conjugate base, however, that's got to be the weaker acid. In other words, H3PO4. Moving on. Has acetic acid versus NH4 plus. So of acetic acid and NH4 plus, acetic acid is definitely the stronger one. And it says which one has a stronger conjugate base. That's got to be the weaker one, the NH4. Now it says HSO4 or HCN. HSO4 or HCN. Let's see them on there. I think we got to go over here. HSO4 negative is here. HCN is here. So of these two, HCN is definitely or HSO4 definitely a stronger acid. It's way up here. It's got a very small very large Ka comparatively. And then stronger conjugate base must be that HCN. All right, guys. Hope this helped. We did the whole thing in about 20 minutes, y'all. You can do this. You've got this. All right, study hard. Bye.